Hello students, welcome. This is the third video on long transmission line analysis. So let us quickly review what we have studied in our previous lecture. At first, we derived the equations for V of x and I of x, right? These equations are valid at any point on the transmission line. Mark my words, these are valid at any point on the transmission line. These are not only just for sending end or receiving end. You can calculate at any point. Remember this. And V of x came out to be a1 e power gamma x plus a2 e power minus gamma x, right? And I of x came out to be a1 by zc e power gamma x minus a2 by zc e power minus gamma x. We derived these equations where x is distance from receiving end to sending end. In some reference books, these equations are derived by considering x as a distance from sending end to receiving end. In that case, you will get a minus sign here. So take care of that. Next, what is gamma? Gamma is our propagation constant, which is given by root over z into y, where z and y are impedance and admittance per unit length. Generally, in the case of long transmission lines, per unit length indicates per kilometer. Next, what is ZC? ZC is our characteristic impedance. Which is given by root over Z by Y. If you observe here, I am multiplying numerator and denominator by length. So this comes out to be square root over Z by Y. Whether you multiply or not, the term length will get cancelled automatically. So ZC is independent of length. We can either take per unit length or total impedance and admittance values. Doesn't matter. But while calculating propagation constant, you should take per unit length values. Next, if you observe the equation of V of x, it is having two terms, V1 and V2. And we discussed that V1 is the wave traveling from sending end to receiving end, and V2 is the wave which is traveling from receiving end to sending end. This is called as deflected wave. Right? So, what will happen if load impedance is equal to ZC? I mean, what will happen if load impedance is equal to characteristic impedance in this case? We already discussed all these things in previous lecture. This is just a recap. If ZL is equal to ZC, our term A2 will become 0. If A2 is becoming 0, this indicates there is no reflection. As an observer, what we feel is, if there is no reflection, we will feel that there is no receiving end and the line is going towards infinity. So, if load impedance is equal to characteristic impedance, this kind of line is called as infinite line. Right? Next, after this, we have derived a pi equivalent model of our long transmission line. So what is a pi model? This is z dash, y dash pi 2, y dash pi 2. And what are the ABCD parameters of long transmission line? Cos h comma L, ZC sin h comma L, sin h comma L by ZC, and cos h comma L. The ABCD parameters for pi model are 1 plus y dash z dash by 2, z dash, y dash into 1 plus y dash z dash by 4, and 1 plus y dash z dash by 2. After comparing these two equations, what are the end results? Z dash is equal to z into sin h comma l by gamma l, and y dash by 2 is equal to y by 2 tan h comma l by 2 by gamma l by 2. Is this clear? Next, after this, we solved a problem on long transmission line and we found out that it is very complex to analyze the equations in terms of hyperbolic parameters. So what we did is, we did a Taylor series approximation for this. And what are the end results? After doing the Taylor series approximations, our result came out to be 1 plus yz by 4, z into 1 plus yz by 6, y into 1 plus yz by 6, and 1 plus yz by 4, right? Yeah. In this video, we will be discussing lossless transmission line. So let's start our lecture. So students, what is the meaning of lossless? This is nothing but power or energy loss should be 0. If power loss is equal to 0 in a transmission line, then it is called as lossless transmission line. So how to model this? Students, you know that we derived the equations of long transmission line by considering 4 parameters: resistance, inductance, conductance, and capacitance, susceptance. So if you observe the parameter inductance and capacitance, they will not dissipate energy. They will just convert the energy from electromagnetic form to electrostatic form, and vice versa. The parameters which dissipate the energy are resistors R and G. R and G. If we need to make the transmission line as lossless, what we should do is, we should make R and G is equal to 0. If R and G is equal to 0, then the transmission line is called as lossless transmission line. Is this clear? So R is equal to G equal to 0. Next, we need the ABCD parameters of lossless transmission line. So to calculate the ABCD parameters, we should calculate the parameters, we should calculate propagation constant and characteristic impedance, right? Then only we can go to ABCD parameters. So first, what is propagation constant? Root over z into y. And what is z, students? Z is equal to R plus j omega L. This is per kilometer, and obviously unit will be ohm. Next, if R is equal to 0, what will be the value of z? J omega L, ohm per kilometer. Next, we got z. Next, we need y. What is y? G plus j omega c, mho per kilometer. If G is equal to 0, what will be y? J omega c, mho per kilometer. Remember, L and C are inductance and capacitance per kilometer. Don't forget this. So what will be root over z into y? This is nothing but root over j omega L into j omega c, which is equal to j omega under root L into c radian per kilometer, because here it is omega. Next, we should calculate ZC. What is ZC? Root over Z by Y. So, which is root over j omega L by j omega C is equal to root over L by C, which is purely resistive in nature. How am I telling that this is purely resistive? Students, if you observe the characteristic impedance of a lossy transmission line, this will be R plus j omega L by G plus j omega C. You will be having some angle here and some angle in the denominator also. So at the end you will be getting some angle, and this will be leading in nature, I mean capacitive in nature. But here these are just constants, there is no complex term. That's why ZC is purely resistive. Let me erase this. And it is also called as surge impedance. Surge impedance. So ZC is equal to ZS is equal to root over L by C. ZC is the characteristic impedance where we define this for any transmission line, and ZS is the surge impedance where we define this only for lossless transmission line. But don't remember this definition. Why? Because in many textbooks these words will be used interchangeably, so we will get confused. Just remember characteristic impedance or surge impedance, both are same thing, there is no difference, and the formula is root over L by C in case of lossless transmission line, right? Next, we will discuss something more about this parameter gamma. So you know gamma is propagation constant. For a lossy line, gamma will be root over Z into Y, and this whole term will be complex. So we can write this as alpha plus j beta. In this, alpha is called as attenuation constant and beta is called as phase constant. I will tell you why these names are given. If we see the equation for v of x will be a1 e power gamma x plus a2 e power minus gamma x. I am substituting the value of gamma in this equation. What will be the result? a1 e power alpha plus j beta x plus a2 e power minus of alpha plus j beta x, right? If I expand this, this will be a1 e power alpha x into e power j beta x plus a2 e power minus alpha x into e power minus j beta x. We can write this as a1 e power alpha x at an angle beta x plus a2 e power minus alpha x at an angle minus beta x. Students, if you observe, the term alpha is shaping our amplitude. In other words, it is decreasing our amplitude. That's why this is called as attenuation constant. And the term beta is shaping our phase. That's why this is called as phase constant. Is this okay? Now, if we compare the equation with the gamma of a lossless transmission line, what is gamma? J omega root L into C. Only the term j beta is present. So this is equal to j beta. And what is beta? Omega root L into C. And what is alpha? Which is 0. And it should be 0, right? Why? Because this is a lossless transmission line. So this is equal to j into beta. Now we got our gamma and ZC. To find ABCD parameters, we will substitute these gamma and ZC in our equations. So cos h gamma L, ZC sin h gamma L, sin h gamma L by ZC, cos h gamma L. We will find one by one. First, cos h gamma L. So what is the formula for cos h gamma L? E power gamma L plus e power minus gamma L by 2, right? Substitute gamma is equal to j beta. What this will be? E power j beta L plus e power minus j beta L by 2, which is equal to cos beta L. If you observe, there is no hyperbolic term in this equation. Next, what is sin h gamma L? This is equal to e power gamma L minus e power minus gamma L by 2. Substitute gamma is equal to j beta. So e power j beta L minus e power minus j beta L by 2. This will be j sin beta L, because for the formula of sin beta L, there will be term 2j in the denominator. Since it is absent here, we are bringing j to the right hand side. So we obtained the value for cos h gamma L and sin h gamma L. So I am just substituting these values here. Vs Is is equal to cos beta L, JZC sin beta L, J sin beta L by ZC, cos beta L into VR and IR. Now if I expand this, what will be the equation for Vs? VR cos beta L plus, one second, J IRZC sin beta L. And what will be the equation for IS? I am writing in a reverse order. IR cos beta L plus J VR by ZC sin beta L. Next, students, in the case of lossy transmission line, we analyzed a case. What if ZL is equal to ZC? That is, what will happen if our load impedance is equal to our characteristic impedance. Let us do the same thing here. So this is my load. Current is IR, voltage is VR, and my load impedance is equal to surge impedance, that is ZS. Now, what will be VR? VR will be IR into ZS. And what will be IR? IR will be VR by ZS. We will be using these equations here. Now, let us substitute these things. Vs is equal to VR cos beta L plus J IRZC is nothing but VR sin beta L. Next, IS is equal to IR cos beta L plus J VR by ZC is nothing but IR sin beta L. So this is nothing but VR at an angle beta L. This is nothing but IR at an angle beta L. This is an interesting result. So here the receiving end voltage is VR at an angle 0 degrees, and IR is IR at an angle 0 degree. The receiving end is having unity power factor. Why? Because it is a resistive load. What about sending end? If you observe, sending end voltage and current are having the same angle. So these two are in phase. That is why sending end is also in unity power factor condition. And the magnitude of the sending end voltage is equal to the magnitude of receiving end voltage, and the magnitude of the sending end current is equal to the magnitude of the receiving end current. This is interesting, right? Generally, this is the case of surge impedance loading, where our load is equal to surge impedance. In this case, there will be a flat profile of voltage. That is, voltage at any point will be equal, and that is equal to the load voltage. Don't worry, we will study this in detail when we discuss about surge impedance loading. For now, just remember these equations. Next, students, let us study more about this term beta. So, you will study this in signals and systems. That is, if there is a term e power j omega t, this represents the complex sinusoidal. And what is the time period? This is 2 pi by omega. So this is the time axis. What is the definition of time period? The period after which the wave repeats itself is called as time period, and this is in terms of time because this is the function omega t, omega into t. So let us say the same thing here. Our voltage equation is A1 e power j beta x plus A2 e power minus j beta x, where x is the length. This is a sinusoidal function with respect to length. So here I am defining wavelength, which is equal to 2 pi by beta. What is the definition of wavelength? This is the length axis. The length after which the wave repeats itself is called as wavelength. So this will be lambda, and lambda is equal to 2 pi by beta, right? Next, I am substituting the value of beta here, 2 pi by omega root L into C, that is 2 pi by 2 pi f root LC, which is 1 by f root LC. Next, so what is the velocity of this traveling wave? You can calculate the velocity as displacement by time, right? So what is the distance here? Lambda. And what is the time? The time taken to travel from this point to this point is nothing but time period t. So this will be lambda by t. Velocity is equal to, and 1 by t is nothing but frequency. So lambda into f. The velocity of a traveling wave is wavelength into frequency. So I am taking this frequency term to the left hand side. Lambda into f will be 1 by under root L into C. Remember guys, this L and C are for unit length parameters. From this, our velocity came out to be 1 by under root L into C. Very important. And generally, this will be equal to 3 into 10 power 8 meter per second. Since we are dealing with kilometers, we can write this as 3 into 10 power 5 kilometer per second. And I forgot to mention a point here. The surge impedance will be in the range of 400 to 600 ohm, in the case of overhead transmission line, and this will be in the range of 40 to 60 ohm in the case of underground cables. You should remember this value. And students, this is for now. Let us summarize what we have studied. At first, we have seen the condition for a line to become lossless, and that condition is R is equal to G is equal to 0. By using this, we derived our propagation constant and characteristic impedance. This came out to be J omega under root LC, and ZC came out to be root over L by C, which is purely resistive in nature. And the value of ZC is 400 to 600 ohm for overhead transmission line, and this is between 40 to 60 ohm for underground cables. After this, we derived our ABCD parameters, and they came out to be cos beta L, JZC sin beta L, J sin beta L by ZC, and cos beta L. After this, we have seen a condition. What if load impedance is equal to our surge impedance? And the results sending end voltage is equal to VR at an angle beta L, and sending end current is equal to IR at an angle beta L, where VR and IR are receiving end parameters, and the power factor turned out to be unity. Next, after this, we have seen the definition of beta. What is the physical significance? So wavelength will be 2 pi by beta, which is 1 by f under root L into C, where L and C are the values per kilometer. Next, from this we calculated the velocity of wave, which is 1 by under root LC, and one second. If nothing is mentioned, this is generally equal to wavelength of light, that is 3 into 10 power 8 meter per second, or 3 into 10 power 5 kilometer per second. Is this okay? In the next lecture, we will solve some problems and we will move to wave traveling analysis. Right? Bye. Take care.